Good evening. I love the way everybody just went quiet. It was awesome. My name is William Harris. I'm President and CEO here at Space Center Houston, and I'm absolutely delighted to welcome all of you to our next Thought Leader series for the month of March. For a little bit of house cleaning, if you have a sound-making device, if you could please put it on silent or turn it off, we would sincerely appreciate it. We also have people watching the program this evening online, and I'd like to welcome them as well. Our Thought Leader series is presented by the University of Texas Medical Branch, UTMB, and UTMB is dedicated to improving the lives of people in Texas and around the world, and we're really appreciative of their support of this series. Our free monthly programming brings together the best and brightest minds in space exploration to share the significance of historic missions, the latest news in space, and a look ahead to the future of space travel. Our presentation this evening, Designing for Human Performance, explores how human factors relate to designing spacecraft and spacesuits. This evening we'll learn about the time and intense collaboration needed to build safe, efficient, and productive spacecraft. In ongoing recognition of 20 years of continuous human habitation on the International Space Station, we have themed all of our Thought Leader series around insights from research conducted on the International Space Station. So we'll be celebrating that as a theme in each of our upcoming series. Our 2020 panel of leading science, engineering, and space exploration experts will provide an evening of fascination and information as they tell us how the ISS took shape hundreds of miles above the Earth. I'd now like to welcome to the podium Steve Campbell, Marketing and Communications Vice President of UTMB, to also share a few words of welcome. Steve?
Thank you very much, and let me add my welcome and let you know how absolutely thrilled we are to be able to provide the sponsorship for another Thought Leaders series lecture. We are very proud as UTMB Health to be part of this amazing community and being able to bring their high quality, accessible care close to home and where you live, work, and play. Last month, we mentioned that we would be expanding pediatric services at our Clear Lake Hospital, and we are absolutely thrilled to tell you that the pediatric inpatient unit and our emergency services that we developed in collaboration with Children's Memorial Hermann is up and running and taking care of kids. So we're very excited about that. In honor of Women's History Month, I would also like to recognize the many amazing women who have transformed our understanding of the human body and space exploration as well. With that, I'll quit talking and let's get on to the interesting stuff. Thank you.
Great, thank you, Steve. I'd also like to say a special thank you to our friends at NASA Johnson Space Center. You know that we are the official visitor center for NASA Johnson Space Center, and we're always so honored to interpret the incredible work that the men and women at Johnson Space Center are doing to advance space exploration. But before we get underway with our program this evening, I wanted to tell you a little bit about Space Center Houston. I think you all know that we are a nonprofit organization, as well as being the official visitor center for NASA Johnson Space Center, and we're dedicated to being a dynamic science and space exploration learning destination. And so we really strive to bring you insights and information about the latest in space exploration and how it benefits life here on Earth. I'm delighted to report that we've been enjoying increased attendance. We closed out 2019 with nearly 1.3 million visitors, which was an all-time record for us. And that included nearly 250,000 youth and educators. So we're really committed to being part of the educational infrastructure of Houston and really advancing youth in our community along the STEM pathway. We have over 400 interesting things to see and do through our various exhibits. And I think you saw something kind of large when you drove in tonight. Did you all notice that big rocket? Well, I am excited to say that is a flown SpaceX F9 rocket segment. And that has actually gone to space twice, enabled two missions to space. And we're one of 2 locations in the United States to exhibit one. The other is at SpaceX headquarters in Hawthorne. And so that's part of our, which is very exciting, yes. But this is part of our commitment to interpreting commercial crew and commercial partnerships in the direction that NASA is going in. So that's going to be part of a larger installation that we'll be rolling out in the coming year. But we're so honored and thrilled by this donation from SpaceX to help tell the story of how the commercial sector is helping advance space exploration. The other thing I wanted to mention is that we have quite a year coming up with a lot of new things. We've just opened a great exhibit out front called Bionic Me. I hope you all take some time to explore that. It really looks at how technology is enabling us to function in life when we have physical challenges. We also will be celebrating in the month of May Women in Aerospace. It will be a luncheon we do every other year. And at that luncheon, we'll be honoring Gwen Shotwell, who's the president and COO of SpaceX, Leanne Carrette, who is the CEO of Boeing Space Systems, and our own Ellen Ochoa, former director of NASA Johnson Space Center. That'll be on May 28th. What's also exciting about that day is it's supporting a larger program supported through Boeing called the Girls STEM Pathway, and we are now engaging 1,400 girls and young women a year to encourage them to pursue careers in engineering and science. So those individuals will all participate in a larger mentoring event, as well as these incredible individuals who will be speaking with you this evening. So if any of you are scientists or engineers and would be interested in participating, please see Kimberly or me at the close of the program this evening. So let's get on with this incredible panel and program. I'm absolutely delighted to introduce our moderator for this evening, Dr. Diane Gibbons, who is the founder and CEO of Trumbull Unmanned and also a member of the board of directors of Space Center Houston. Diane studied engineering and learned to fly at the U.S. Air Force Academy. Her PhD research in industrial engineering and management focused on unmanned aircraft systems. In 2019, she founded Trumbull Unmanned, which uses advanced unmanned aircraft systems in the oil and gas industry, acquiring data through drones and turning it into valuable information. Diane was named one of the women shaping the drone industry by Fortune magazine, and as an emerging veteran tech founder by the Huffington Post. Please join me in welcoming Diane Gibbons, who will introduce the panel. Thank you.
Thank you. I do have to say, I did not finish my PhD. I did all the coursework, and I'm not in the club. But thank you. It did sound nice. It did sound nice. I will say. And so it is absolutely a pleasure to be here with you at Space Center Houston. Thank you all for coming. Excited to be here with you, celebrating these amazing women as part of this Thought Leader series. And thank you again to our sponsor for having this. I did want to ask a few questions of the audience just to gauge who's here. So if you could, by a show of hands, who was here in July for the 50th anniversary of the moon landing? Raise them high. That is a good amount. Wonderful. I was here too. Who was here for Galaxy Lights, the first year of Galaxy Lights here? Raise them high. How many of you are the same people that were here in July? Okay, a lot of the same people. Perfect. And how many of you are members here at Space Center Houston? Wonderful. If you're not a member, I would consider you joining. Every time I'm here, I feel like a kid. And that's with my 7-year-old daughter and our son as well. So I'm very happy you're here. Happy you're here for this series. I think you're in for a treat. I'm excited to hear from these amazing women. And so thank you again for the introduction. And first, I will introduce Celena, who will present, and then we'll have Katie present. We'll go into discussion after that, Q&A, and then open it up for audience Q&A, who will send their questions to thoughtleaders@spacecenter.org. So now I'm going to introduce Celena. Celena Dopart is a human factors systems engineer for Boeing in Houston. She earned her Bachelor of Science in Aerospace Engineering from WPI in 2012, and her Master of Science in Aeronautics and Astronautics from MIT in 2014. Her master's research focused on aerospace human factors, specifically astronaut jetpacks. Seriously. She does nothing with jetpacks anymore, though, but likes to relive her glory days while getting introduced at speaking events. Before joining Boeing, and this is a real bio, I'm not ad-libbing up here and making this up. Before joining Boeing, Celena was a serial adult intern at the European Astronaut Center in Cologne, Germany, in the astronaut training division, and then was NASA's Johnson Space Center in the Extravehicular Activity Operations Group. Now going on 5 years at Boeing, she supports the development, test, and operations of the CST-100 Starliner spacecraft. I'll stop here so she has something to talk about during today. Thank you. Please welcome me, or join me in welcoming Celena.
Hi, everyone. Thank you, Diane, for that wonderful introduction. So I'm Celena Dopart. I work for Boeing. I'm a human factors systems engineer, and I have control of the slides. So before I start, what is the Starliner? I'm sure that a lot of you here, because you're here, you know what the Starliner is and what the commercial crew program is. But for those of you who might not be aware, I'll just give you the little primer. The Starliner is a next generation spacecraft that is going to take American astronauts to and from the International Space Station from American soil. Since the shuttle retired in 2011, NASA astronauts have hitched rides on the Russian Soyuz capsule. It has served us very well for the past few years, but NASA wants to bring that capability back to the United States. And so that's where Boeing comes in. We are building the Starliner to do just that. For those of you, again, who follow our program, you probably know that we just completed our first test flight to space in December, the orbital flight test. There were no humans on board, but we did have an anthropometric test mannequin named Rosie the Rocketeer. She was wired up with sensors to bring back information about what a human would feel on board our spacecraft. And we also had her co-pilot, Snoopy. He's the one who got to have fun in the pilot seat floating around in microgravity. So before I really get into human factors, I'm going to give you a sneak peek, a public sneak peek at their flight. That is really cool on a big screen. It's a little dizzying, honestly. I know you feel like you're there. So I wasn't at launch, but I was at landing, and it does, seeing it on the big screen like this, it really does feel like you're there. So now I guarantee the rest of my presentation is not that cool, but I'm going to talk to you about what human factor systems engineering is and how it helps us get from a conceptual design to what you just saw on the screen. So Human factor systems engineering, in short, is designing a system that's three things: effective, efficient, and safe for the human user that will use it. In our case, that's the astronauts. So here on the left, we have Chris Ferguson. He is the first commercial astronaut. He works for Boeing. He's a former NASA astronaut. He retired, and he's spending his retirement as the Director of Crew and Mission Systems at Boeing. He will be commanding our first crewed test flight. And on the right, we've got his crew members, Nicole Mann and Mike Fink, and then the backup CFT crew member, Butch Wilmore. And so when we're thinking about the design of a system, we think about these guys and gals who are going to be flying on it. All right, so we think about them. We want to design a system that's safe, efficient, and effective for these astronauts. But how do we do that in practice? So I'm going to give you the how-to, step-by-step guide to design a system that's effective, efficient, and safe for a human user. Step one, think about it from the human's perspective. It sounds really simple. It can be harder in practice. A spacecraft is very complicated, but there are a lot of questions that we can ask to help guide us through this process. So we're going to go through a few of them. Who am I? Here we have our CFT crew members. They're getting ready for a training event. They've all got different backgrounds. They are all NASA astronauts or have been a NASA astronaut. They're all test pilots, but you can see here they're different heights. They do have different backgrounds, and we're not just catering towards NASA astronauts. Right now, we are designing a vehicle to fly NASA astronauts to and from the International Space Station, but in the future, we hope to expand it to the general public as well. Maybe the rich general public in the near future term. But so we're thinking about that first and foremost. Who are the people who are going to be flying on our spacecraft? What are the tasks that those crew members are going to have to perform? So when we start thinking about a conceptual mission, we start thinking about these questions. We know we're designing a spacecraft. We know the general mission. We're going to space station and we're coming back. But what are the tasks that the crew member on board the spacecraft is going to have to perform in order to do that? If everything goes nominal, we have a pretty good idea of what they're going to have to do. What about when something goes wrong? You got to think through all of those as well. When do they have to perform these tasks? Is there a time limit to the tasks that they have to perform? What type of environment are they performing it under? So do they have to perform a certain task under the loads of launch, under the vibrations of launch? Do they have to perform it in microgravity where they're floating around and they don't have anything keeping them strapped to the seat? Or are they doing it under re-entry loads and then on landing? What sort of configuration? Are they wearing a suit? Are they in a seat? Are all of them out of their seats at the same time trying to fight each other for space? These are all sorts of questions that we have to ask to help define this mission that we're building the spacecraft for. What about the physical demands that this crew is going to meet during the tasks that they're performing, and the mental demands? So this could be as simple as reaching out and touching a button or actuating a switch. It could be more complicated. In a contingency landing scenario, what are the physical tasks that we're asking them to perform, and how do we prepare them for that? And how do we design a system to enable the performance we're asking of them? And what about the skills? Do we have to train it? Do they already come with those skills? Right now, with the NASA Astronaut Corps that we are designing this vehicle for, we have a pretty good idea of what they're coming to the table with. But again, in the future, that answer to that question might change. What about assistance? Do they have anybody to help them through these tasks? Do they have their comm cap on with MCC, Mission Control Center here in Houston, in their ear, helping them work through the nominal mission tasks or through a failure response? And do they have other crew members on board to help them through all these tasks? For most of the nominal missions that we are planning on flying for NASA, it's probably going to be 4 crew members on board. This first one is going to be free as our test flight. But we have a requirement from NASA to fly 0 to 4 crew members. So what if we fly a scenario where there's 1 crew member on board and they have to do everything, but we design the spacecraft for 4 people? How do we make sure that this 1 crew member will be able to do everything that they need to do? So it's a lot of questions. It's a lot kind of all at once, but that's what the design process is. You start thinking small little questions, and then you come back to them again and again. So we take these questions and we ask them about the piece parts that we're trying to design. So we think about a subsystem or one piece of hardware, and we ask all those questions, and we start thinking about how to optimize the design for that human user. So let's think through some of them. The buttons, switches, and valves that they might have to interface with, or the displays and controls. So in the photo, you see one of our, he's our PCM1 pilot, Josh. He is doing a task on our instrument and control panel. How did we design all those buttons and the displays to make sure it's optimized for him? Part of it, you can see it's kind of wrapped around the commander's seat. Now, he's sitting in Sonny Williams' seat right now. I will say he's the pilot, Sonny's the commander. So, but they are both helping to evaluate our design. And so we wrap the console around that seat one so that that single crew member can reach everything that they need to on the panel. The displays, they have to give enough information without giving too much information so that they're overloaded with too much. The suit and the seat interfaces. So this is Chris getting suited up for a training event. The suit and the seat are both designed with human protection in mind. So they are there to make sure that the human is safe, but they also are going to be sitting in them for quite a while, so they have to be comfortable, and they have to serve different purposes in different scenarios. So we think through all of that, and again, optimize the design for the human user. Some of the items that you might not think about as being part of a spacecraft design are operational items, things like tablets that house all the procedures that the crew is going to use, cameras and wireless access points to be able to use the tablets with some of the other systems, and the unglamorous hygiene equipment, and then the food and the water to sustain the crew on their journey to station. All of these things, again, optimized for the crew. And finally, the things that we don't want to ever think about, we never want to use, but we have to make sure are designed flawlessly for the human user. So these are some of our contingency emergency items that only in the case of something going really, really wrong would the crew ever use. But in the event of something like that happening, it needs to be easy, it needs to be quick, and the crew needs to be able to use it either based on training or intuition. And so the design of those systems is really, really important too, even though we hope the crew never has to touch them. So step 3, then we go back. We've got some great pieces of hardware, some great subsystems designed perfectly for the human user. But we have to go in again and ask a bunch more questions about how it fits into the larger system. So what if we take one of those piece parts and use it with another system? Let's think again about the seat and the suit. We know we designed the seat perfectly to be able to fit every range of crew member that NASA laid out in the requirements document, from the shortest to the tallest, people with the longest arms, the longest legs, the shortest torsos, every combination you can think of. That suit fits, that seat and the suit fits them. But what about when we put that seat into the spacecraft? Do the rest of the systems, the closeouts that are covering up some of our wiring and computers, the console that we saw as a piece part that Josh was evaluating, when you put those together, do their knees start bumping the console and stuff like that? So those are some of the sorts of questions that you have to think about once you design these pieces of hardware. And I will say, this all happens at the same time. It's cycles, it's iterative. We can't do things in these easy step 1, step 2, step 3, because we'll get to this step and realize we thought about it all wrong. But this is kind of the guide, and then we iterate. Yeah, that is me at the back of my head. Yeah. Yeah, that's over in Building 9, our Boeing mock-up trainer. This is a suited egress test that we were doing. So speaking of egress, perfect segue. What do we do in an emergency situation or an off-nominal situation? We got to think about all those things, and what happens when one part fails? Can the rest of the system compensate for it? Can the crew compensate for it? And even astronauts are humans, and they make mistakes. And so does the system, the design of the system that we just created, support those sorts of scenarios? So we ask all those questions, all the previous questions. At every level, we go back, we ask them again, we do it again and again and again, and ta-da, we've got a spacecraft. It's that easy. So we've got our conceptual design, we've got some stuff down on paper, we've got some mock-ups built, maybe some simulators. Is our job done? You guys all know the answer to that. Of course not. Like I already kind of spilled the beans, we just iterate over and over again. We go through this cycle. That is what systems engineering is. And we do a lot of analysis, we do a lot of evaluations. We bring the astronauts in to serve as test subjects and consultants on our program. We make sure that this design is going to work for that end user by bringing them in early. And we do a lot of testing, and we do a lot more iterating. And at every step of this design cycle, the design gets closer and closer to, quote, perfect. And it also gets harder and harder to change. Because the better a system is, the more integrated it is. And the more integrated it is, you change one thing and it waterfalls. So we start getting creative with the ways we address different issues. But ultimately, we go back always to the end user. How is the astronaut going to be using this vehicle? And that's basically the overarching design principle that helps us get, again, from this conceptual stage to flying. So we will keep on iterating, because that's how you get from here. This is baby Celena when she was less than a year at Boeing at our old mock-up. This is one of the first ones we had. It's at the KSC Visitor Center, so if you're ever in Florida, you can go see this one. We did our early human factors evaluations in this one. To here, this is the BMT over in Building 9. We're still doing engineering evaluations in it, but we also did the majority of our human-in-the-loop requirement verification for our program in this vehicle with astronauts and engineers. We even have a test subject over there. To this is our environmental qualification test article. So this was the first time I got to get into one of our spacecraft, and we did more interface testing in here to kind of convince ourselves that what we were testing over in Building 9 with our mock-up was really close to flight, so the results were valid. And finally, to here. This is post-landing after our spacecraft came back. This is Calypso. And this was immediately after landing. I opened the hatch and I was the first one in. I performed, again, some human factors testing, because we never stopped testing, we never stopped iterating and improving the design. And so that's the face of someone very pleased and very relieved to have performed a good post-landing operation. Thank you very much.
Wonderful job, Celena. I did enjoy all the pictures of you. And your mother, if she's watching right now, I'm not sure. So thank you for the presentation. We're going to shift gears now, and Katie will present, and I will read her bio. Katie will come up, and then we'll proceed to the discussion and Q&A. And again, if you have questions you would like to be asked, please send those to thoughtleaders@spacecenter.org. Katie Spira is an Ethos Environmental Systems NASA flight controller. She received her bachelor's degree in mechanical engineering from the United States Coast Guard Academy, a friend of the Air Force Academy, and was selected as commanding officer of the Coast Guard cutter Haddock, an 87-foot patrol boat stationed in San Diego, California. There she commanded the ship and crew through multiple counter-narcotic and search and rescue cases, preventing the entry of over 18,000 pounds of marijuana, my first bio to ever include marijuana in reading that, so we get to participate in that together, and the rescue of over 12 lives at sea. That's impressive. Upon completion of her assignment on Coast Guard cutter Haddock, Katie transitioned out of the military and pursued her master's degree in aerospace engineering at Texas A&M University. Pause. I'm waiting for the whoop or, okay. Someone always says it. After graduation, Katie began work as a flight controller for the International Space Station at Johnson Space Center in Houston, Texas. She currently has her back room certification and is in training for her front room flight controller certification. Again, if you have questions, please send those to thoughtleaders@spacecenter.org. Katie, over to you.
Good evening, everyone. Thank you guys for coming and listening about this. I've got a few bio slides just to share my background since it's a little crazy, and then we'll get into the human factors perspective from the ISS program perspective. So as they mentioned, I'm originally from Sanger, Texas. I have a bachelor's degree in mechanical engineering from the Coast Guard Academy, and then, as she stated, master's from A&M. Okay, see, you were the warm-up for it, thanks. For military experience, I started out Key West, Florida. Not the worst location to do a duty rotation, I will say. Student engineer on that platform, and then I actually got to go deploy to a combat zone over in Manama, Bahrain, and do a year tour out there. The Coast Guard actually does deploy to the Middle East. And then I was very fortunate to be given command of my own ship, and so you can see dress whites. Love that picture. And then now I am here as an ISS flight controller. I did have some experience with NASA. Growing up, I was able to do the high school aerospace scholars program, class of 2006. It's a great program where kids from high school come in, spend a week, learn about NASA, different programs. So it's a great introduction and a great way to get their feet wet in the program. So to the topic of tonight for human factors. So being a flight controller, and especially in the ethos branch, we focus on environmental systems, and so that's heavy interaction with crew. And so why do we do these things? We do it because of these men and women right here. This is the most recently graduated class of astronauts, and they are the difference between satellites and these human vehicles, right? So you're still going to have propulsion, you're still going to have guidance on rockets, but the big difference is humans. And so if I can have you take anything away from this presentation, because I'm still learning every day about how you take things almost for granted in the 1G environment, things that we have access to, things that we can do, things that we can just throw away that you can't do in space, so it's a very interesting concept. So again, anything with humans, we have to have this component where we account for a human cargo, if you will, on board. So as you can see, all these vehicles are going to be future carriers of humans to space. So I don't have a cool video, but I have a spaghetti graph. So I'm going to try and explain this piece by piece to you guys. So let's think about what a human actually needs to live. You need a suitable atmosphere, a suitable pressure. You need to be able to breathe, and you need to be able to eat, drink. Sorry, Netflix is not in the list. So let's start with water. How do we drink in space? How do we get water to space? If the about average is about $50,000 to launch 1 pound of cargo to space, varies depending which vehicle you're on. We're not going to be launching bottles of Evian water, or I guess Dasani is our sponsor tonight, up every time the astronauts get thirsty. So we have to figure out a way how to make water on board. And how we do that is partially through astronaut urine. We'll just jump right into that topic. So we're able to process it and produce a water product that is further purified down into drinkable water. So this is what we call closing the loop. And hopefully we want to completely close the loop so that we can have self-sustaining or as close as possible members in space. That's going to enable us to do long duration space flights. That's going to enable us to go further and further out and explore. Also, I mentioned that we need to be able to breathe. So we actually do have an oxygen generator on board the ISS. It takes that water that we have and it splits it, and it gives us oxygen as well. So we're able to replenish the oxygen that the crew breathes down. And so with crew breathing, a big component of when you exhale is carbon dioxide. For us on Earth, we exhale and it goes into the atmosphere, we're fine. Where does it go on the space station? It's a closed can, so it continually builds up, and we have to figure out a way how to filter out that carbon dioxide. So that's another unit that we have on board that actually takes down, scrubs out the carbon dioxide and keeps the atmosphere pure for our astronauts, as pure as possible. And then of course, you're in the extreme environment of space. We have to maintain that pressure so that people can live. So we have to have the ability to introduce gas into the space station, keep it up at a habitable pressure. And we also have to make sure vacuum of space is pretty cold. And if you're in direct sunlight, that's pretty hot. So we have to have a good kind of temperate climate for our astronauts so that they can actually be comfortable and perform their main focus of the mission, which is going to be payloads and science. Another thing that I think is really interesting, who vacuums their house? Oh, okay, wow, not a lot of people. All right, no judgment. But all of your dust, all your particles, right? It falls on the floor, vacuum it up. And no gravity, it all kind of like floats with you. So you have to find a way, okay, we're going to have air drawing in, a filtration system that is going to, filter out those particles. So there's a lot of things, and I'm constantly amazed. Oh, why can't the astronauts just like push on this harder? Well, they're just going to push away. And so that kind of worked for the fade out too. And so there's a lot of components that I think are very, very interesting. And this is why I love my job so much, because again, it's the biggest difference between satellites. We have to account for our living cargo on board. All right, enough of the spaghetti slide. So these are the subsystems that my discipline actually breaks down on how we try and account for those human factors. I'll go through each of them individually, but as you can see, there's a lot of stuff that we maintain and a lot that tags in with your presentation as well. So again, we got our ACS, our atmosphere control and supply. So we're able to introduce gas, able to control how much O2 and N2 is in the stack, and keep it as close to near Earth levels as possible. And then we also have additional gas support to users. Some of the payloads use oxygen on board or nitrogen as part of their experiments, so we are able to provide that. We have fire detection and suppression. There is a lot of equipment running up there, a lot of stuff, and so you need to be able to detect when there is potentially an emergency situation. You need to be able to suppress it with a fire extinguisher or some other means, and you need to be able to have the hardware to actually respond to that. Protective mass, essentially the fire extinguishers as well. AR, atmosphere revitalization. So we need to be able to see what is in our systems and what are bad components and scrub those out as well. So we have a bunch of equipment, as I said, scrubbing out CO2 and any other kind of byproducts that come. Then we have THC. That's going to supply our atmosphere, our temperature regulation, and again, that airflow so that we're getting good mixing throughout the stack. Yeah, different kind of THC. Thank you. I can tell you're not obsessed with this topic at all. Another thing that we do as well is internal thermal control systems. So for the internal thermal control systems, we help cool the payloads, right? Those things generate a lot of heat, power, so we help cool those. That's also part of what helps us keep the astronauts cool. We have a cooling loop, and those go over a fan, and so if they say, hey, we're a little warm, we're able to turn the thermostat, the space thermostat down, if you will. And then we've also got a vacuum system, which this so much isn't for the human factors, but it enables us to do science, to conduct experiments, so that people are able to vent like exhaust gases overboard. The big one that we were talking about was regenerative ecolith. So this is, making today's coffee into tomorrow's coffee. Not that quickly, but you get the point. And then also providing them with oxygen. We have passive thermal control. So again, with the great varying temperatures, we need to make sure that we don't unknowingly condense on the walls, right? That would be really gross, and microbes would grow. So we want to try and control that shell temperature of the ISS as best as possible. Obviously, you've got to have good plumbing. And then, as we all say, you don't want it to ever happen, but you always need to be prepared for an emergency response on board. So we have several emergency scenarios that we frequently plan for, both in simulations with the crew, with the flight control teams, to make sure that on the unfortunate, very bad day that we do run into those events, that we are able to respond calm, coolly, collectively, and get the job accomplished. So to give you an example of how this works, we'll start from the very top. So we'll call it crew inputs, urine, and that gets processed through the urine processor assembly. That produces, as I said, almost a potable water quality, but it is further processed down, and so that becomes potable water for the crew. That potable water is then filtered to downstream users, the crew, anybody else that needs it, plants that they're growing up in space, as well to our oxygen generation assembly. And that, again, puts O2 back into the stack, which the astronauts are constantly breathing down. And then, of course, we have our carbon dioxide scrubbing. So that's kind of a visual of how we make it all come together. And, of course, supporting the astronauts, making that happen, we have a fantastic team who works day and night for training the astronauts, training the flight controllers so that we are all able to make this incredible mission happen. So that's the environmental systems perspective of human factors engineering. So thank you guys.
Thank you for your presentation. How do you hear me? Loud and clear. No more jokes tonight. It's all serious from here on out. I'm just kidding. So now we're going to transition into our discussion. One more question for the audience. So who again was here in July for the 50th anniversary? Who came on the day? Okay, of those, except for William, who remembers the band who headlined that night? Who can say it? 2 points for you. Good job. All right. Moving on to our conversation. Just keep you engaged. Oh yeah, any students in the audience? Raise your hand, please. Great. Well, thank your parents for bringing you here on a school night. So we'll try and make this relevant for you as well. Okay, so transitioning into questions. First question is, how are the astronauts involved in the development and improvement of technologies on board? So everyone's take that first.
I'll start that one. I talked about it a little bit in my slides tonight, but the crew has been really involved. We are very lucky to be right down the street. We're a couple of miles away from here. So we are very involved with the NASA Astronaut Corps, and they work really closely with us. So I mentioned them as sort of test subjects, but also consultants. The commercial crew cadre, the 5 of them who were announced, I think, in 2015, because it was right before I started at Boeing, they have been part of our design process since that time. So that includes the guys who went over to SpaceX and are going to be flying on their first crew, as well as the ones who have been assigned to our first flights. They have been helping us in the simulations, in each of those mock-ups that I showed you, and in the spacecraft. We bring them in as often as possible to make sure they have visibility into what we're doing, and we have the insight that they have from their years of experience of actually flying in space. So all the things that we can only imagine and think about, they have actually done. So they give us invaluable information to help us design the spacecraft. So that's kind of from the early side of things. That's how they have been involved in helping define the technology through the design process.
Yeah, and from the ISS perspective, one unique opportunity that we have that's amazing is sometime after a crew comes back from orbit, they'll actually meet with several divisions and talk about any inputs that they had for the system. So I was fortunate to be able to go to one of those ones and hear the crew members. First, it was really cool to see them in person. Normally you just see them on the cameras when you're working console. But hear them saying, hey, that box that's running, it runs a lot louder than you think it does. And you go, oh, okay, well maybe we'll run that only during the crew wake period instead of the crew night. Like things that you don't even think about in the design process. Or, hey, the pictures in this procedure weren't really helpful, we want you to put this there or capture this image of this. And so they're able to give you a lot, and we're very thankful for that opportunity, because we're basically able, as you said, to reiterate and iterate on the process to make the products better for our crews.
And we will eventually have that as well once we fly a crew. Snoopy didn't tell us anything when he came back. Rosie did. We're still processing that data, so I don't know much about what she told us. But when we do fly real humans who can speak to us, we will have debriefs like that. And so, again, that design process will continue to be iterative.
Thank you both. And again, if you have questions after this, we'll move into audience Q&A. Please send those to thoughtleaders@spacecenter.org. Okay, next question. How do the facilities at NASA JSC, simulators, mock-ups, mission control, help design for human performance?
So I'll start off if you don't mind. So speaking from the simulation side, the instructors do a great job of throwing us, I would say, the meanest cases they could possibly throw at us to see how we adapt and how we make our priorities as far as tackling failures, right? And we're always told you have the crew, the mission, and the vehicle and the mission. Wow, I'm messing it up. And so the crew is always at the forefront, and they do a great job of doing that. And so when you get all these cases, you have to adapt to that. And then more from the crew perspective, as you mentioned, Building 9 is a great mock-up facility. I'm not sure if anyone's been over to Building 9, and it's where they have that almost full-size mock-up of the International Space Station. And so they're very high-fidelity models in there. They look a lot like what's on orbit, and members of the Ethos branch are able to conduct trainings with crew, and they're able to run through actual scenarios, even emergency scenarios, and get their inputs, different training techniques, different factors, and that great resource of the building.
I love hearing this because this is what we're going to end up doing eventually once we become a sustaining program. That's the way we're going to use the simulations with MCC and the way we're going to use our current trainer. Right now, the way we use it is kind of what I shared in the slides. We do a lot of human-in-the-loop evaluations and testing. We did a lot of our requirement verification in Building 9 in our mock-up, and we've got other trainers and simulators on site at NASA as well. We do use MCC as well, and we have simulators over in Building 5, which is the training building. And so we do the same thing, but with crew. We throw at them whatever failures we can to see how they respond, and we also do that with our control team as well to give them training, just like it's the real thing. So the facilities at NASA look really cool, but they also serve a real great purpose for us.
And so you mentioned in the loop. Can you maybe just briefly share, in the loop, on the loop, out of the loop? I imagine many people know.
Yeah,
what that
so a
means.
lot
If you
of,
could just
We
explain
want to
that.
be in the loop.
some of you may be out of
Some
the
may be
loop
out of the
about
loop, yes.
loop speaking. But so MCC, I honestly don't know what I just said to phrase in the loop or on the loop, but basically Mission Control Center will be in communication with the crew who's on the vehicle. And so when you're talking, and I think I mentioned when they've got the comm cap on or when they're talking through the speaker system, they've got MCC in their ear. They are on the loops with MCC. And so we can have a full conversation with the crew to find out where they are, what they're doing, what steps they're taking, and then the ground Mission Control Center, our flight controllers, can help them do their job better.
Perfect. Who is your favorite astronaut actor? I'm kidding. Fake question, fake question. Okay, real question. What role do operations... You can say it if you want. Just kidding. What role do operations and procedures play in designing for human performance? You can answer either question, whichever one.
You mentioned this a little bit earlier with the pictures and stuff. Want to expand on that a little?
Yeah, so our procedures just aren't text, which is a really cool option that we have. We have a bunch of pictures in there. So that helps crew because a lot of times, an astronaut training program is probably 8 to 10 years long. And they may see something 5 years ago, and then the next time they see it, it's actually on orbit. So those procedures with pictures can really, really help. There's also... one thing that I think is really cool, the interface that we have for procedures is actually has like a highlighter bar that the crew can just push the down arrow key and it keeps with their number in the procedure. Like that's a simple thing that seems easy, but you wouldn't think about in the design process, oh yeah, I'll be able to read the procedure. Then you go away, you do something and you go, wait, did I do step 5 or was that step 4? So it's a cool, they just put that highlight bar there. So you have these procedures and they're robust and we're able to update them relatively quickly to meet any needs of the crew or if there's better options for it.
And in our design process, I mentioned in that design cycle, the iterative cycle, the closer we get to a final design, the harder it is to change it. So something we can do if we do find something that isn't working with our system or something that we didn't think about when we were finishing the design of a certain piece of hardware or subcomponent, we can use the crew and we can use operations and procedures to kind of serve as a control for a design feature, let's call it. So we use the crew a lot, and we use operations, training, and procedures to kind of get that design from the 99% to the 100%.
Thank you. Back to students. Can the students please raise their hand again? Perfect. And so for students in here, for students on the line, parents, can you share more on your education playing a role in getting to where you are now? And then, at what moment was it real for you that you'd be supporting NASA?
I'll start. So I've been obsessed with space since I was really little. And so I grew up knowing I wanted to do something in the space field. So when I was looking at colleges, I knew I wanted to be an engineer. I knew I wanted to study aerospace engineering. So I specifically looked at colleges that offered that type of program, and not just mechanical with an aerospace concentration, but a full-up aerospace engineering program. So that's how I ended up at WPI. And when I went to MIT for grad school, my advisor was an astronaut. And I remember just getting an email being like, this is your assigned advisor. And I went to look him up on Wikipedia, I Googled him, and it was a former astronaut. I'm like, all right, well, this is the coolest thing that's ever happened. And so I kind of I fell into human factors engineering. I knew I wanted to work in the space field. I knew I wanted to do something systems level because I didn't want to just be a GNC person or just be a propulsion person. I wanted to get that systems level look at things. And so they just happened to assign me to Jeff Hoffman, my advisor. And I was part of the Manned Vehicle Lab, which is now more gender neutral, the Human Systems Lab, which they should have done a long time ago. But I just, again, fell into human factors. I was in a lab that focused on the human systems interface for aerospace engineering, and that ended up being the perfect little niche for me within the aerospace field. And I knew when I left, I wanted to work in human space exploration. I didn't just want to do satellites or something. I wanted to get that human cargo on board. And
The most precious cargo.
yeah, the most precious cargo of all. And so I mean, again, through my serial adult internships, I got to kind of bounce around a couple different space centers, and that was really cool as well. But I ended up here at Boeing doing pretty much my dream job, helping astronauts get back to space from American soil.
Now I really regret you going first. Gotta go fast. I did not always know that I wanted to work in the space field or that I would ever be in this job. I honestly did not think I was smart enough because I really struggled in school. At the Coast Guard Academy, you have to meet certain grade thresholds every semester to stay in your major, and there was more than one occasion I was very, very close. So I almost think more what I got out of my education was the fight, the want to stay in. I know I want to do mechanical engineering. I know that I'm capable of this, studying long, hard nights, trying to get that degree and get through. And so it ended up coming together very, very nicely.
You broke your own glass ceiling.
I guess. Yeah. And so I just remember thinking like, oh my God, everyone's completely brilliant at NASA. And I'm not saying that they're not, but I was like, no, there's no room for me. I can't do this. But then when I started my master's degree at A&M, I actually had a former astronaut. It's fine.
I was ready for that.
We had a former astronaut, Dr. Chamitoff, as one of our teachers, and he was teaching us kind of an introduction to how actually space works, right? How the ISS works, how we get people up there, how that ISS functions with all the different console positions that you see in mission control. And so then I started thinking about this whole operational side. I'd only realized, I think, really the engineering side, see the Apollo 13 movie and they said the round can and the square, and trying to put that together. I'm like, I don't want to do that. I'm not smart enough. But then I said, wait, operations. I've deployed overseas. I've, commanded a ship. I think I can do that. And then you realize there's this whole other entity. And then even in that, you realize there's even more to it at NASA. So it's not just engineers and people crunching numbers behind computers. So I think the struggles that I had initially really cemented that work ethic. And, if you really want something, it doesn't matter how difficult it is, just fully commit to it, nose to the grindstone, get it done. And then realizing there's actually so much more to NASA than just strict designing a product from, square one.
Good job. That's worth it.
And I will say, imposter syndrome is a very real thing. So any of you students out there, if you haven't heard of it, look into it because everybody's got it.
I second that motion. Thank you both for sharing that. And I like, Katie, how you also just broadened out what supporting NASA means. And I think that, opens up a lot of fields for people that they may not have realized that they can support NASA. And so I'm happy you shared that. And I know at the Air Force Academy, we have at least a human factors concentration. I think it's under behavioral science. I'm assuming the Coast Guard Academy has something similar.
We only have 8 majors.
Really? Okay.
We're tiny.
Okay. No, that's great. Well, so I think at most of the service academies, they'll have, engineering, systems engineering, aeronautics, aerospace, all the others. And so I'm excited to learn more about the Coast Guard Academy majors. And if you're interested, come up after, and you can learn the 7 others. Okay. Next question, which maybe I think our last question before we go to the Q&A. How do you adapt your systems to each individual crew? Can you share more about what that means? You first, Katie.
So one thing that I think is extremely fascinating, like I said, I'm constantly being surprised by my job, and I've been in it for 2 years, is how each crew is different. And that sounds really obvious, but also think about the spaghetti graph, your favorite graph. Different crews produce different urine rates, right? They consume oxygen at different rates. And so we're constantly adapting, figuring out, okay, this is what this crew's average metabolic rates look like, and this is how we have to adjust our systems. So I always think that's super fascinating when they come on board. You've got a bunch of flux in all of our rates, and then things settle out, and you're like, oh, okay, like this 4 crew actually drinks water like their 3.5 crew. They output urine at like 5.5 crew, and so it's very interesting to see that fluctuation with metabolic rates as their bodies do indeed change when they get to space and settle out. So
That's so interesting. Yeah, so we actually have similar. You reminded me that post-landing, we land in the desert. It's really dry out there. And this past flight, we didn't have any crew. Rosie and Snoopy didn't sweat at all. So it was really dry in there, and we have to worry about ESD, so shocking things, and damaging electronic hardware. With the crew on board, it's probably going to be more human in the spacecraft. So in some instances, the crew will help solve some of our problems. But also some of the other more obvious things, I think, just the different sizes of the crew members. I talked about the different configurations. We can fly anywhere from 0 to 4 crew members. So each mission, the configuration is going to be different. We're going to be carrying different size crews in the different seat positions. We're going to be carrying different cargo loads, and all of that. It's a very fun game of Tetris that we're going to have to do every mission.
And for the young students, Tetris is a game that was on Game Boy and others. Okay, perfect. So I think those are the questions we have dozens of more questions, but we don't have that much time. But we do want to move on to audience Q&A. And again, if you have questions, please send them to thoughtleaders@spacecenter.org. So please continue to send those. Kimberly, I believe you'll share some questions, and we'll go through the audience Q&A, and then you can ask Celena her favorite astronaut actor afterwards. Okay, Kimberly.
All right, the first one is for Katie from your bio. Can you tell us what is a backdoor and front door certification?
did it say back door or back room? I hope it said back room. So sorry. What a typo. So for you guys are familiar, or hopefully you're familiar with the Mission Control Center, and you see all those console positions. So those are what we like to call front room flight controllers. And those flight controllers are responsible for coordinating amongst the other disciplines and keeping that big picture situational awareness of what's going on. But behind each of those individuals, not literally, but like in another room in another part of the building, there's 1 to 3, depending on what console it is, backroom positions that are actually supporting that front room. So the front room's trying to think, okay, I need to decide between A and B, and the back room comes in the ear and said, all right, so here's the stats for A, you can do this, 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 and this if we choose option A, and you can do this, this, this if you choose option B. So it's interesting because the back room almost gives you more of the technical aspect of it. That's their job, to focus on the details of the response that you're working at that time. And the front room weighs what's the needs of the overall room are, and then can make the executive decision for that console. And then of course the flight director itself makes the final decision for the room. So right now I have my back room certification and am working my way to get my front room certification.
So you guys talk in the loops, on the loops, out of the loop?
All the loops.
All right, this one's for Celena. Can you tell us, is the Starliner reusable? And how many crew members does it hold?
That's a great question. Two great questions. Yes, the Starliner is reusable. So I wish I had a graphic up there, but there's two parts to a Starliner. There's kind of the conical capsule shape on top and then the cylindrical shape on the bottom. And the conical part is the crew module. That's where the crew sits. That's the habitable volume. And underneath it, that's the service module. That's a lot of the propulsion, the big stuff that gives our orbital maneuvers and all that sort of stuff. The service module is not reusable, but the crew module is, I think, up to 10 times. And so I don't know if you guys saw this in the news, but post-landing after our OFT flight, Sunny was out in the field with us, and she named that capsule Calypso because she's going to be the commander of the next mission that flies that capsule. So we are going to reuse that capsule multiple times. And then the other question, how many crew do we carry? The NASA requirement says that we should be able to carry anywhere from 0 to 4 crew members. Our first crewed flight test will carry 3 crew members, and that 4th seat will be filled with cargo. But then in the future, we do have the configuration right now on board to carry 5. And so it's going to take, again, some more Tetris, and we actually have our mass properties lead here, and that's going to be a big job for her, figuring out what goes where to make sure that all these different configurations still meet our CG requirements and all of those requirements.
Great. All right, either of you, to what extent do psychological factors drive spacecraft design?
I'll start with this one, with Starliner. So our missions are really short for Starliner in terms of how long they'll be flying on our capsule. We are planning on flying primarily NASA astronauts to and from the International Space Station. So for the most part, they will be going on long duration missions, but they'll be on the Starliner from anywhere from 8 hours to a couple of days. So there's not too much time to get super bored or go crazy like in The Martian or whatever. But I think we do have to think a lot about the mental demands that we have on the crew. Because like I said, you're probably not going to get bored, but if you have nothing to do, you might. And then if something goes wrong, you might not be in the mindset to be able to respond to it. So as a human factors engineer, we do think a lot about what we call the workload, the mental workload. And that's basically how you manage different tasks and how to design a system to make sure that you can manage all those different things. And it helps if you've got multiple people on board to entertain yourself, but also help out with the tasks that you do have to complete.
The only thing that I think I could add from an ethos perspective for psychological is how we plan our maintenance activities. So obviously some of this equipment has been up there for 10, 15 years and it needs to be serviced. And so we not only factor in like the lifetime of the product, but crew availability. They're busy completing science, that's their purpose on board. And so we try and space those out and put them at such intervals that it's also convenient for crew, but we don't risk hardware damage or hardware failure.
Great. Can you tell us about a time where you had a situation that stumped you? And can you tell us about that process and what the end result was?
This question's stumping me.
Or it goes a little bit further, or something where you overcomplicated a solution and then you ended up having to go back finding a simpler solution.
I can talk about a simulation case that I was in that I looked like a ripe idiot. So I saw like a quantity falling on a tank and I feel like, okay, we have this gas leak overboard. I know what to do. And it's almost like a training scar, as we used to call it. Like you get so used to responding to some cases, you see a little bit of data and you're like, oh, it's that case. I know what to do. I'm going to do it until it's wrong. And then you get to go to the flight loop and say that you're wrong and then recover because you're like, oh, we didn't leak 50 pounds of gas overboard. Our sensor biased, so we're totally fine, but the sensor doesn't tell us what we have in the tank anymore.
So I think part of the reason why that question is hard is because even though you say you're wrong, you had a thought process to get to that point and you worked through it to get to the right answer. And I think that's part of engineering and systems engineering is getting stumped and then figuring it out. So I think it's hard to pinpoint an exact scenario where that happened, but I'm sure it happens all the time. But the whole point is to work through it and make sure that the next iteration won't stump you.
And at least from the flight controller perspective, that's almost kind of the purpose of sims. They'll throw everything at you but the kitchen sink, and your first few, you're just kind of deer in the headlights, like, okay, you know, and like following direction and trying to get things done, and you're like, I think I can, and then you find your groove, and then you start getting ahead of the problem, and you're like, okay, if this happens, then I need to work this on my day, because we're not going to be able to do those activities. And so you almost work through that getting stumped feeling. You can get overwhelmed, especially initially in training or in the first part of a design process, but by chipping away a little piece at it, you kind of prevent that.
You get really comfortable at being wrong.
Great. Can you talk about any machine learning, data analytics, or artificial intelligence that you might use in your work?
No, I wish we did. I wish I could.
I can share something briefly.
Yeah.
Well, so there's Trumbull and Man, which I lead, and then we just started a company called Sail Analytics. And so my partner, Uri, he was an Air Force test pilot, U-2, F-16, Global Hawk. MIT, started at MIT, but then 3Ds from Columbia. And so we support machine learning, artificial intelligence, primarily in Department of Defense. We just got an Air Force contract we're excited about, but also in the energy sector. And so in the energy sector, we're reviewing data for a super major or one of the largest companies on how we can assess and review the data to provide actual recommendations and some perhaps predictive recommendations as well. We're also working with Draper. I saw you were there. So that's a couple areas where we're using it, but you guys, I'm sure, are using it in many, 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 many ways with what you're doing or what your companies are doing. It's the future. It's the future.
It is the future. And yeah, if we're doing it on our program, I don't know about it. So you guys just stumped me.
Well, there you go. That was the other one. Yeah.
All right. This is, let's see, question for Katie. Can you tell us a little bit more about the astronauts on the space station? They ask about if an astronaut gets sick, or you talked about them and how each crew is different. Can you just tell us a little bit more about them living on space and the different things that you all have to think through? For instance, them getting sick. What do you do?
So as far as for a crew getting sick, that's going to be out of my realm of responsibility. We have a position called flight surgeon, call them the flight doc, who specifically works, and they know each crew member really well. And at any point, a crew member can say, hey, I want to talk to my doc, and we'll make the phone call happen. And then that way they can get the medical perspective that they need. From an ethos perspective, I think I'll just tackle this more for a handover, since we're coming close to a handover period now on the ISS. Obviously, new crew members coming on board, they have to get used to being in space, one, and then learn their job responsibilities. And there's not always a lot of time to hand that over, right? If you're replacing somebody a job, sometimes they're still there, sometimes you get a direct handover, and sometimes they were gone months before you, and you got to kind of figure it out. Well, we don't want that to happen, because it's a $100 billion spacecraft orbiting 250 miles above our head, going 17,500 miles per hour. We don't want to mess things up, and we want to make sure that they can perform all the duties that they need to keep their mission sustained. And so we actually have these handover periods where, like, if an activity for the crew member takes 30 minutes, we'll actually schedule them 45 or 50 minutes, and they'll be paired with a crew member who's been on the space station for a while. And they'll actually do kind of a direct handover of like, oh no, yeah, this valve's a little squeaky, so you got to do this. And so they can pass all the nuances that we don't have on the ground. So that's how we kind of get them up to speed. So I approached it more from that aspect than the medical one, which I can't really speak to, but hopefully that answered your question.
I'll add just a tiny bit to that. So the Starliner, I mentioned that it takes NASA astronauts up there for a long duration mission, but the Starliner itself is really only used for the period of getting up there and then coming back. While it's docked to station, it does serve a purpose. It's just a passive purpose. it is there as a lifeboat. So if we have some sort of emergency or if a crew member gets sick, we can bring them back really quickly with our visiting vehicle that's docked to space station.
Great. All right, last question. This is from a 6-year-old Roman. He wants to know, what is the coolest thing about working at NASA or with NASA?
Two things. One is Ryan Gosling sometimes. So that's what
This
that
may have answered the question. The mystery is.
I was telling a story about how I was at the space vehicle mock-up facility over at NASA doing some training, and they told us don't go anywhere that you're not cleared for today, and it was because Ryan Gosling was there. So that's why he's my favorite astronaut actor. But really the coolest part is the astronauts. We get to work with them, and that is so cool. Growing up with them kind of as the idols, they're almost, I don't know, they're bigger than life. They are celebrities, but then you come here and they're your colleagues, and you're working right next to them, and they're helping you design, and you're helping them work through the operation. So that is incredible, and I pinch myself every day that I get to work with them.
Since she took 2, I'm gonna do 2 as well. So number 1, the people. I still remember, like, sometimes I would make like a space joke on the ship and they would make fun of me. Well, they don't do that here because everybody makes those space jokes. And so I love that. And then really one of the things that like drew me to the Coast Guard was that every day was different, right? You're on the water, sometimes you're at the pier, some days you're just punching holes in the water, some days you're chasing down drug runners. But it kind of carries over to this job. Every day I am surprised, and I love that. Every day I learn something new about what we do, the capabilities, how far-reaching, what programs we actually have, and it just always surprises me, and I love it. And then sometimes you do some things that completely surprise yourself. There was once I was on console, and there was I don't know how to say it, a real false fire enunciate. And so it was just a telemetry issue. It tripped the fire message, but there was no fire on board. And it was funny because I'm like, boom, this procedure, this is what we're going to do. And like, here's the readings. And you're like, oh, wow, that training really did work. And you know, it's never what you expect. And I love going to work every day being surprised.
Well, thank you. I think that concludes our Q&A. That concludes our panel. I want to say thank you. I know Willem's going to say a few words for attending. Thank you for your questions. I know we solved the mystery of the favorite astronaut actor. If you want to know the other 7 majors or any other questions, please come up. I did also want to say, UTMB, Willem, hand it over to you. Thank you.
Great. Thank you so much, Diane. Please give them all a round of applause. It was absolutely a fascinating discussion. Thank you so much for being here this evening. We really value all that you do to make successful our space program. And we look forward to having you participate in future panels with us here at Space Center Houston. I want to remind everyone that we have another very special panel coming up in April. I think, as you know, and we referenced this during the panel, that we're coming up in the 50th anniversary of the Apollo 13 experience. And I'm very, very excited to announce that on April 15th, we'll have a very special panel with none other than Fred Hayes, who was the pilot in Apollo 13, and also Gene Kranz and Glenn Lunny, who are also flight directors from the Apollo era. And so they'll be here to kind of share their experiences and interact with the audience. I think some of you may or may not know that we have quite a few artifacts from the Apollo 13 mission here at Space Center Houston in our Starship Gallery. In fact, we actually have the scrubber box that the flight controllers and engineers designed and put together and coached the crew on developing to save their lives, to scrub the carbon dioxide from the air. So that'll be featured as part of that evening program. So again, thank you for coming out this evening, and we look forward to seeing you at our next Thought Leaders program. Have a great evening.